Hey everyone, how's it going? I hope that you are well. I want to welcome you to Chapter 10, Lecture 1. And this lecture is entitled Introduction to Logistic Regression. So what's logistic regression? Well, before I answer that question, let's back up a little bit to Chapter 9, where we learned about multiple regression analysis. And you'll recall that multiple regression analysis employs multiple independent variables simultaneously to predict a dependent variable y. And you'll also recall that the dependent variable y in multiple regression has to be either ordinal or scale level and normally distributed. And that's because it is a parametric test. It is predicated on the normal distribution. Well, you might be thinking multiple regression is pretty cool, and I can see how that would be a useful technique for prediction or explanation. But what if the outcome that I'm interested in is not normally distributed? What if the outcome that I'm interested in predicting or explaining has only two categories? Yes, no, either or, this or that. Obviously, in such a situation, you couldn't use multiple regression. So what can you use? Well, the option under those circumstances is to use a statistical technique referred to as logistic regression analysis. And that's what we'll be looking at in this lecture series corresponding to Chapter 10 of the textbook, which you'll see in the following slide. Is, as always, the textbook that we're using in this lecture series and that we're using as part of this course, this Applied Data Analysis course. The textbook is entitled Applied Statistics, Business and Management Research, and it was written by yours truly. Now, before proceeding with this lecture series, I would urge you to read Chapter 10 first rather than jump right into this lecture series, because reading it will give you a better understanding of the concepts that I'll be talking about throughout the rest of this lecture. All right, so if you'd like to learn about logistic regression analysis, then how about we just jump right in? Let's do it. Okay, logistic regression can be either bivariate, close to simple regression or similar to simple regression, with only one x variable and one y variable, or it can be multivariate, similar to multiple regression. And that is, it includes multiple x variables simultaneously to predict your outcome y. But in this case, in this particular technique, the dependent variable has to be a two-category nominal variable. If it's not a two-category nominal variable, then you are sadly unable to use this technique. But this is a useful technique because you can imagine that there's any number of questions in life where you'd like an either or prediction, a this way or that way prediction. Like multiple regression, it has multiple uses. You can use logistic regression for purposes of prediction. So in that case, you might ask yourself, how likely is outcome A or outcome B given a particular situation? What's the likelihood of outcome A versus B? You can also use logistic regression analysis for purposes of explanation. So when you're using it for purposes of explanation, the question you're looking at is, how does a one unit change in your independent variable x impact the odds of y, your outcome, happening? So as x moves up, do the odds of y happening move up? Do they move down, or do they stay the same? So that's effectively how you explain the relationship between each x in your equation and your outcome y. You can also fruitfully use logistic regression analysis for purposes of classification. So classification is essentially a situation where you have a set of predictors. So for example, x1, x2, x3, all the way up to xy. And given this set of predictors, you're asking, does a respondent most likely belong in group A or group B? In other words, can we classify this individual according to outcome A or according to outcome B, given the inputs in the logistic regression equation? So it's a perfect technique, especially for instances where you'd simply like to predict yes or no outcomes. Again, it's not possible to do that in the context of multiple regression analysis. Let's take a few moments to compare and contrast logistic regression with multiple regression. All right, so I've articulated a few points here that I think are salient to this discussion. The first point is that similar to what you learned about in multiple regression, the independent variables in logistic regression can also be scale level, they can be ordinal, or they can be two-category, that is to say, dummy variables. So the configuration of independent variables is essentially the same across logistic regression and multiple regression. And really the only type of variable that's excluded from both equations or both techniques is a multi-category nominal variable. That is to say, a nominal variable with 3 or more categories. But as we learned about in the previous lecture, it's possible to take a multi-category nominal variable and convert it into a series of dichotomous or dummy variables so that you can incorporate that into your equations. Multiple regression is based on the logic of what we call ordinary least squares. And what ordinary least squares is that it's essentially the technique that we use to identify the line of best fit, the line that best fits the data, that minimizes the residuals or errors between each data point and the line of best fit. And of course, multiple regression is also predicated on a normal distribution. The dependent variable in multiple regression, as we've learned, always has to be either ordinal or preferably scale. And the reason is that multiple regression is a parametric statistical test. It's predicated on a normal distribution. So your dependent variable has to conform to that necessity, to that regulation. Logistic regression, unlike multiple regression, doesn't use ordinary least squares logic. Instead, it uses a technique called maximum likelihood estimation, also abbreviated as MLE. And this is a technique that is based on probabilities, essentially. And it uses MLE in order to calculate the coefficients. So just like with multiple regression, there were B coefficients. Well, there are also B coefficients in logistic regression, except these coefficients are based on an S-shaped probability distribution. So if that's not clear, don't worry, because it will become clear over the next couple slides what I mean by an S-shaped probability distribution. And as I said, the key difference between logistic regression and multiple regression is that logistic regression must only have two outcomes for the dependent variable. Yes or no, either or, this or that. Now you might be thinking at this point, why do I have to learn another statistical technique? I just spent a lot of time figuring out multiple regression. Why can't I just use the multiple regression techniques in order to predict a binary variable, in order to predict a two-category nominal variable? Well, the answer is you could if you wanted, right? But the problem is if you did that, if you use multiple regression to predict an either or outcome, your results could be nonsensical. And the example that I'm giving here, I think, illustrates why that is the case. So first thing, let's have a look at the graphs on the right-hand side. At the top, you can see an example of ordinary least squared multiple regression predicting an either or outcome. And on the bottom, you can see a logistic regression predicting an either or outcome. So what we're predicting here is the relationship between years of education and employment status, where 1 equals the individual is in paid employment and 0 equals the individual is not in paid employment. So the fact is, when you're dealing with these types of variables, you're either employed or you're not employed. It's that simple, right? You can't be more than fully employed and you can't be less than unemployed. So there is a ceiling and there is a floor for this particular outcome. And the problem is, if you use OLS to predict a two-category outcome, you can still produce a line of best fit, as you can see in the top right-hand corner, right? You can see a line showing a positive relationship across those two outcomes, but it's a nonsensical line because you can see it extends above in paid employment as well as below not in paid employment. In other words, the line of best fit will continue to infinity. Now, in logistic regression, rather than using a single line of best fit, a straight line, we use something called a sigmoid distribution, a sigmoid line, which is that S-shaped line to the right there on the bottom right-hand corner of the slide. And the advantage of using a sigmoid line is that you can see it draws a definite top at fully employed as well as a definite bottom at unemployed. So you can see that, yes, it is possible to use multiple regression to predict a two-category outcome, but it likely won't make any sense, and therefore it's best to use logistic regression instead. All right, let's take a few moments to operationalize some research questions. These are research questions that you could ask as well as answer using logistic regression analysis. So you'll find that across these research questions, these examples that we're going to go through in the next couple slides, by definition, what we're predicting has a two-category outcome, either or, option A or option B. So let's start with the first question here. What are the predictors of the likelihood that a Hollywood movie will turn a profit or not? You could see how this could be a useful research question to ask if you work in the movie industry, right? If you are a producer of movies, you want to make sure that the movies that you produce are profitable. Otherwise, you make a loss. So it is possible to build a logistic regression model predicting this particular outcome. And the outcome is whether or not your movie will turn a profit. So what are some potential predictors that you could posit that might predict this outcome? So I've given you an example of 4 possible predictors here. We have number 1, the total production budget, right? So you want to have perhaps a bigger budget might be generally associated with greater success in terms of profit. Obviously, there will be exceptions. There are small budget films that turn huge profits, and there are huge budget films that make a loss. But generally speaking, there's a certain sweet spot where you have to put enough money into a production in order for it to have the emotional effect on the audience. So that might be X1. That's a scale level variable, so the amount of money that you put in. Second, whether or not the movie features an Academy Award winning actor. So that's a binary, a dummy variable. And you could probably reason that if the movie features an Academy Award winning actor, then it's likely to go on to turn a profit. Again, no guarantees here. We're dealing in probabilities, but without an Academy Award winning actor, it may be a more difficult climb. The next possible predictor here is the total length of the movie. So that's X3. Perhaps very, very long movies might turn people off. You know, if you do a movie that's 4 or 5 hours, that might be too long, but there probably is some kind of sweet spot. At the same time, if the movie's too short, you probably fail in terms of character development and being able to connect with your audience in terms of the characters that you've created. So that might be another predictor. Again, that's a scale level variable. You can measure it in minutes. The next predictor might be the audience reaction to the trailer, right? So you might show the audience a trailer and ask them to rate it on a scale of 1 to 7, where 1 equals this movie looks boring to 7, this movie looks awesome. So you combine all four of these predictors into a logistic regression equation, and what you're trying to predict in this case is the dependent variable y, which is whether the sampled movies made a profit or a loss. All right, let's look at the next potential research question that we could ask and answer using logistic regression. What are the predictors of the likelihood that a job applicant will be successful in a job interview? So in this case, our key outcome is whether or not an individual was successful in a job interview. It clearly conforms to the requirements of logistic regression because the outcome variable, the dependent variable, is binary. It's dichotomous. It's either you succeeded or you didn't succeed. So I've listed out again a series of potential predictors that you could put into a logistic regression equation. Maybe the percentage of time making eye contact, that would be x1. That's a scale level variable. You make good eye contact, you might be more likely to be successful. Job applicant attractiveness rated on a scale of 1 to 7, where 1 is not at all attractive and 7 is extremely attractive. So you might assume that more attractive applicants are more likely to get a job offer at the end of an interview. Height might be another one. So this is another scale level variable. You could measure it in inches or centimeters or however you want to measure it. And you might assume that taller people are more likely to be successful in a job interview than shorter people. Whether the applicant has a 4-year degree, so here's a dummy variable, a dichotomous variable, which you could ask, do you have a 4-year degree, yes or no? That would be x4. X5 might be whether the applicant has relevant training to the job itself. So that would be another dummy variable, either yes or no. And 6 might be whether the applicant already has social connections within the company, right? So this is another dummy variable, either yes, I do have connections already in the company, or no, I don't. And you can probably assume that if you do have connections, you're more likely to succeed in the job interview. So again, in this case, the dependent variable y is whether the applicant was successful in the interview. All right, let's take a look at one last example of a research question that you could answer using logistic regression. What are the predictors of the likelihood that a patient will live or die? Now, obviously, this would be an important question if you're in the field of medicine. If you're a doctor or, for example, a hospital administrator, this might be useful information to have at your disposal. So what you could do is to design a multiple logistic regression equation that incorporates the following predictors. So you might include age as a predictor. That would be x1. Age is a scale level variable, right? So older patients might have a greater likelihood of dying than younger patients. Gender might be relevant, so that's a dummy variable, a binary variable. You could call that x2. Mental health might be relevant. So if you had some kind of measure of a patient's mental health, how they're traveling mentally at a particular time, maybe that's a ordinal level variable, like how do you feel on a scale of 1 to 10 or 1 to 20 or whatever scale you use. That might be a relevant predictor. Obviously, if you're in good mental health, you might be less likely to die. How about whether the patient is diabetic? So here's another binary variable, another dichotomous variable. Either you have diabetes or you don't. Weight might be a relevant predictor, right? So this is a scale level variable. Whether the patient is taking a particular medication, right? So pharmaceutical industries might be particularly relevant in this predictor, right? So are you taking this medication, yes or no? And how does that impact your chances of living or dying in the hospital? Number of days of hospitalization. So there's another scale level variable. Obviously, the longer you're in the hospital, maybe the greater likelihood that you won't make it. And how about whether the patient has health insurance? So that's X8. That might be more relevant for an example in a country like the United States than a country like the UK or Australia, where we have universal health care. The dependent variable, of course, as I've said, is Y, and in this case, it's whether the sample patients lived or died. All right, thank you very much for your time. I hope you learned a little something about logistic regression, and I look forward to seeing you at lecture 2 corresponding to chapter 10, where we'll go into a bit more depth surrounding the concept of probabilities and odds, because these are central to the technique. See you in a bit. Bye-bye.